Ready?
Okay. Hello, good afternoon, everyone. I'm Jie Liu, the future of the fellow from cohort 3, and work with Kristen and Professor Wang. Yeah, they're both my supervisors. Two professors are my supervisors, and this is one of the piece of my work for my fellowship, and we intend to use the historical flooding event record and using the rainfall precipitation inquiries through the weather station ahead of the observation time, as well as using some topographic features alongside the road and on the road to do the prediction. So we intend to predict where the flood will occur and how severe the flood it is. And first, I'd like to introduce about the basic data that we use to do the prediction. This data is sourced from geotechnical drainage management service system from National Highway with more than 35,000 historical flood events. These are the details of the data set, and it recorded the location, and it also recorded the flood observation time, and it also tells us about the flood severity index. It quantifies the flood severity. I will talk about later about this index. So you will find that this index is the aggregated index. It not only directly reflects the flood impact. The lower two are related to the flood impact. It's the maximum effect on carriageway, its closure or its partial closure. It's also for the fellow criteria, it's the duration of the impact. But for this indicator, it also included the road level and the chest flow, and so it's the aggregated indicator here. So based on this indicator, so if we want to do the flood severity index prediction, we should include those criteria in our feature in our machine learning model. So we trying to get all related features to help us to do the prediction. And first, we're using this API from the Department for Environment, Food and Rural Affairs to get the precipitation rate. Then, because our historical flood event giving us the location and the time where the flooding occurs, so we get using API to retrieve the precipitation rate ahead of the flood observation time. So for each location, there are so many weather stations. So we trying to find the nearest one close to the flood location. This is the flood precipitation that we encourage through the website, and we encourage the precipitation ahead of the observation time for 3 hours, 6 hours, and 2 hours, because maybe our in the historical flood event recording, maybe it has some delays. So we trying to get the precipitation rate for different time windows ahead of the observation time. And for the topographic features, it also can affect the flood severity. So we're trying to based on two data sets. One is the digital terrain elevation, and the other one is the digital surface elevation. We use those two data sets to compute some topographic features like the roughness and slope. And we can also know whether the road is above the ground level or lower, above or below the ground level. So this is the process, and how can we get the topographic features. And first, we load the flood location, and we generate the points alongside on the road, and we also generate the points for the road surroundings, and then we can compute the topographic features on the road and alongside the road, and using the mean value, fifths and lattice and as well as the standard deviation of those values to represent the topographic features. And we also included the road level and flows in our machine learning models. So those three different attributes are included in our machine learning model to do the flood prediction. And initially, we use different basic machine learning models to do the prediction. We found that the random forest is powerful for predicting the non-severe flood events, but the catboat has strengths in predicting the severe flood event. So gradually, we found that we can try to propose this framework to integrate different models together to give us the final prediction value about the flood severity index. So the first step is the data process. I won't talk about it. For the second one, that is the Gaussian mixture model to classify the features of the and trying to make that the feature space into two latent regimes and assign different routing probabilities. These probabilities will be used in the step 4. For the step 3, we use different machine learning models and to train the different machine learning models to get the best one. And then for the soft aggregation, we use the because we use different models to do the prediction, we can get the values for different models. And for the step 2, we get the probabilities of the routing. And then, so in the step 4, we use a soft weighting derived from the routing probability, and the value of predicted by the different models then get the final result about the flood severity index. This is our comparison for our proposed model and other models, and we do the comparison not only for different data sets. One is for the all samples. That means we don't care about how severe the flood it is. We put all the data set together to train the model, and we found that random forest is the best one because large amount of the historical flood event belong to the non-severe event. So the random forest performs the best. But our proposed model, if we only focus on the predicting the severe flood event, I think that there are transport operators and managers more concerned about the severe flood event. And based on the National Highways report, they treated that flood severity index over 6 as the severe flood event. So we, for those events, we do the prediction for them, and we found our model is better. This is the root mean square error that just giving the more penalty to the large errors. We get the similar conclusion that for overall predicting, random forest still be the best one, but for the severe flood event, our proposed model would be the best one. And this figure this figure further shows that for different flood severity beams, that the prediction performers, if the flood severity index is less than 6, and this time our model perform is not the best one, but over the 6, you will see that the red line shows the lowest the absolute mean error. And this is the figure that give us the general information about the predicted value and the recorded historical flood severity index value. The R square means that if the predicted value equals the observed value, the R square would be the would equal 1. But you will see that this figure shows our proposed model. Our model still shows the improved alignments in the upper range. You will see that for those models here, for the severe event, typically it's not close to the line, but this one is more close to the line. So our models still have some strength in the severe flood event prediction. In this figure, we just treated the problem as binary prediction, which means that we just predict whether this flood event would be the severe or non-severe. And the red line still shows that our model would be the best one. And this figure shows the importance of different features. The upper three, the most important features, the rainfall precipitation, and the fourth one is related to the flood risk. And there are also some features that are related to the road level as well as the topographic features are really critical for our prediction. Okay, that's all. That's my presentation. Thank you.